Possible roots. We're going to continue to look at roots from our polynomial functions. So say we have a function, f of x. It is a cubic function, so we know it has to have 3 roots by the fundamental theorem of algebra. And we can use our Descartes rule of signs to find out more information about that. Now to do that, we need to find f of negative x, which I found below. And then looking at our sign changes, so in our f of x, we can see there's no sign change here, no sign change here. And here's a sign change. So it must have one positive real root. Looking at f of negative x, we can see we have one sign change, 2 sign changes. So we know that it has 2 or 0 negative real roots. And we can use the fact that we know that it has to be 3 total roots to figure out how many imaginary roots they have, that this function may have. So we know it has to have one positive, and if it has 2 negative, that gives me a total of 3. So I know my imaginary roots are going to be 0 if this is the case. If I have one positive root, which I always do, and I have 0 negative real roots, then I know I must have those 2 imaginary roots to give me a total of 3 roots. Now this tells us a little bit about our real and imaginary roots. What numbers should we try to figure out what the roots are? I mean, of course we want to try things like 1 and 2, some nice numbers, but we know we could have square roots in there that are also roots. And so our next thing we're going to explore is a different kind of number that's going to tell us a little bit more about the possible roots. So first let's kind of review what real numbers are. So real numbers include pi, include plus and minus rad 5, they include decimals, repeating or non-repeating, they include all of the integers, -2, 1, 0, 3 halves. Those are all included in the real numbers. So when I'm solving for solutions and I use the quadratic formula and I don't get a nice number under that square root sign, that's still a real number. However, it's not rational. So there's a subset of my real numbers that are rational. And it's more specific. So it doesn't include things like the square root of 5 or pi. It has to be able to be written as a fraction of integers. So like 3 halves without the denominator being 0. Imaginary, now when we talk about imaginary over here, we're also including things with an imaginary part. So although this is a complex number, it includes that imaginary part. It's this set of rational numbers that I'm interested in for the rational root theorem. So what the rational root theorem says is the possible rational roots in f of x are in the reduced form plus and minus p over q. That p and that q are just standing for different things, where p is a factor of the constant in my polynomial and q is a factor of the leading coefficient. So here's my constant in this polynomial and here's my leading coefficient. If we take all of the factors of 10 over all of the factors of 3 in various combinations, those are my possible rational roots. I can't have any other rational roots except for the factors of 10 over the factors of 3, and it's plus and minus. So to kind of get those, I have all of the factors of 10 listed up here and all of the factors of 3. And I can just go ahead and go through them, making this fraction, this p over q. So 5 over 1, plus and minus 5 over 1 is a possible rational root. Plus and minus 2 over 1, plus or minus 1 over 1, plus or minus 10 over 1. And I can do the same thing now with 3. Plus and minus 5 over 3, plus and minus 2 over 3, plus and minus 1 over 3, and plus and minus 10 over 3. And so all of these are possible rational roots. Now there could be some other real roots in there with square roots, but those are the only possible rational roots. Now let's see how that comes into play when looking at a polynomial function. So here I have a different polynomial function. It's a quartic, so I know there has to be a total of 4 roots. Now first I can kind of categorize those roots, those possible roots, by using Descartes' rule of signs, in which case I also need f of negative x. So let's first look at f of x. My sign changes, I have 1 here and then I have another here and another. So I have a total of 3. So I could have 3 or 1 possible positive real roots. Now let's look at negative possibilities. So I'm going to look at f of negative x. And here I only have one sign change right here. So that one sign change tells me I have to have a negative real root. Doesn't have to necessarily be rational, but I definitely have one negative real root. My imaginary roots I'm going to get just from looking at my total and combining my possible positive real roots and my possible negative real roots. So here I've got 3. If I have 3 positive and 1 negative, I know I'm going to have 0 imaginary because that gives me my 4 total. However, if I have 1 positive real and 1 negative real, I only have 2, and I need to account for that in my imaginary. So it's possible I could have 2 imaginary. Now let's go ahead and use the rational root theorem to look at my possible rational roots. So to do that, I want to look at the factors of my constant right here over the factors of my leading coefficient, that 4 right there. So putting all of my factors of this constant term, I have 1 and 6, because 1 times 6 is 6, and 2 and 3. Those are all my factors of 6. My factors of 4 are 1, 2, and 4. And then looking at the possible combinations, I'm going to go ahead and start over here with my 1. So I have plus and minus 1 over 1, that's here, plus and minus 1 over 2, plus and minus 1 over 4. And then I'm going to go ahead and look at the 6, plus and minus 6 over 1, plus and minus 6 over 2, which is just 3 over 1, plus and minus 6 over 4, which is really just the same as 3 halves, so plus and minus 3 halves. Do the same thing with the 2, plus and minus 2 over 1, plus and minus 2 over 2, which is the same as 1 over 1, plus and minus 2 over 4, which is the same as plus and minus 1 half. Same thing with 3. Plus or minus 3 over 1, plus or minus 3 over 2, which I have over here already, and plus or minus 3 over 4. So those are my possibilities. When I'm testing for roots, I'm going to use these to help me out because I don't have a list of all the possible irrational roots. I only have a possibility of rational roots. So these are the numbers I'm going to try. So I've just transcribed them up to the top. And I've made them a little bit easier. Instead of plus or minus 1 over 1, I just put plus or minus 1. So these are my possibilities. And when I'm looking to see if something is a root or a factor of it, I can go ahead and use synthetic division. So I've written the coefficients of my polynomial up top. And this is the root I'm going to try, this 1. Now I can try positive or negative 1. I often try 1 because 1's pretty easy to work with, especially when doing synthetic division. So I always, if it's a possible root, I'm going to give it a try. So here I have my 1, I bring down my 4, 4 times 1 is 4, add them, I have a negative 9 times 1 is negative 9, add them, negative 22 times 1 is negative 22, add them, and I have a 6, 6 times 1 is just a positive 6, add them together, negative 6 plus 6 is a 0, so I know 1 is a root and x minus 1 is a factor. Now, when I have one of these roots, I can use this polynomial instead of my big long polynomial. This has one less term here to find some of my other roots. So if I want to test 2, I can just use this depressed polynomial. So I've rewritten it up here, and I'm going to try a 2. So bring down the 4. 4 times 2 is 8. Add them, negative 1. Negative 1 times 2 is negative 2. Add them, negative 24. Negative 24 times 2 is negative 48. I can tell already this is not going to be a root. Add them, and I get negative 42. So I know 2 is not a root, even though it was one of my possibilities. So 2 is not a root. However, I do know that 2 comma negative 42 is a point on my graph. So this is a point I could use if I were graphing this polynomial function. So you would go through these and try some of the ones. I usually try the easy ones first, the plus and minus 1 and the 2. Descartes' rule of science helps you kind of guess that, but the problem is it also includes those real roots as well as the plus and minus, the irrational ones, plus and minus square root of 5 and different other things. I tried a 1/4 because I've done this problem before, but you would probably try several others before you tried 1/4. Just want to show you what happens with the 1/4. And I'm using that depressed polynomial from up here. So that's that same depressed polynomial I rewrote up here. 1/4, bring down the 4. 4 times 1/4 is 1. Add them, -8. -8 times 1/4 is -2. Add them, -24. -24 times 1/4 is going to give me a -6. Add them, and I have a 0. So I know 1/4 is a root. Now the great thing about it when I get to here is this is a depressed polynomial, and it's a special depressed polynomial because it's quadratic. This is 4x squared minus 8x minus 24. And anytime I get a polynomial in the form of a quadratic, I know how to solve that. I can either factor it, complete the square, or use the quadratic formula. So rewriting this up here, and then I just went ahead and divided everything by a 4, and then used the quadratic formula, and then reduce. There's a couple steps in there, but you go ahead and do all of this stuff under the polynomial, and you can pull out a 2, and then simplify that, and we have 1 plus and minus rad 7. This gives me 2 different roots. I have my root over here, 1, and I also have 1/4. So I have a total of 4 roots, and if you go back, you can see that's one of my possibilities. I have 3 positive real roots, 1 plus rad 7, 1 and 1/4, and I have 1 negative real root, 1 minus rad 7. That's definitely, this rad 7 is definitely bigger than 1, so that's going to be a negative number. So I have no imaginary roots in this case. So you can use the rational root theorem to find possibilities that you can test with your synthetic division. Always remember to use that depressed polynomial at the end. That just makes it easier and it makes it more efficient to get to that quadratic.